Hello and welcome to the final round of logistic regression. So let's recap what we did in the previous tutorials. We started by pre-processing our data using our data pre-processing template, and that made our data set ready to fit the logistic regression to our training set, which is what we did in this step. Then we used this logistic regression classifier to predict the test set results so that we can evaluate the predicting power of our logistic regression model. And then indeed we made this confusion matrix to actually count all the correct predictions and the incorrect predictions. And now we're at the final step, which is to visualize the training set results and the test set results as well. And now we're eventually at the final round of our logistic regression model, which is the fun part. Because we're going to visualize the training set results as well as the test set results. And basically we're going to make a plot that will represent everything that is happening with our logistic regression model. So let's make this chart. I'm going to do like in Python. I'm going to take the code that I've prepared and paste it here. I will select and execute the code. And then for those of you who are interested in the idea behind the code, that is how the code plots the graph, I will explain how the code works at the end of this tutorial. Okay, so let's do it. Let's start getting the fun. Okay, so right now I'm going to paste the code. Here we go. Okay, so the first thing to do here is to notice that there is this lmstatlearn package that you need to install if it's not in your packages here. So as you can see, it's in my packages list because I installed it before. If it's not here, you need to install it. So to install it, you will need to remove this comment. And you type install.packages and then in parentheses lmstatlearn, that's the name of the package, in quotes. Then you select this line and execute. And right now, as you can see, it's installing the package. And now the package is installed. I didn't have to do it because it was already installed, but that was just to show you. And now we're ready to select the code and execute it. And that is even if it's not selected here because I put the library lmstatlearn, which once executed will activate this package. We'll select it. Okay, then this code contains 15 lines of code. That was also the case in Python, and that's because it's the exact same code based on the same idea. And I will explain this idea. That means I will explain how this code works at the end of this tutorial. But for now, let's select this code and let's see what happens. So Command and Control plus Enter to execute, and let's wait. It's taking a little time, that's normal, but it's going to plot something. There it is. There it is. That's the plot. Okay, so for those of you who followed the Python tutorial, we obtain exactly the same plot. So let's describe this plot. I'm going to enlarge this. Okay, so let's analyze this graph step by step. First, let's focus on all the points here. We can see that we have some red points and some green points. So all these points that we see on this graph are the observation points of our training set. That is, these are all the users of the social network that were selected to go to the training set. And each of these users here is characterized by its age here on the x-axis and its estimated salary here on the y-axis. Now, we can see that there are some red points here and some green points here. The red points are the training set observations for which the dependent variable purchased is equal to 0. And the green points are the training set observations for which the dependent variable purchased is equal to 1. That means that the red points here are the users who didn't buy the SUV, and the green points here are the users who actually bought the SUV. So now, as a first step of analysis, let's give an interpretation of what we observe here with these users. Okay, so first, we can see that the users who are young with a low estimated salary, so these users here, actually didn't buy the SUV. Then if we look at the users who are older and with a higher estimated salary, well, we can see that most of these users actually bought the SUV. And it actually makes sense because the SUV is more like a family car and therefore more interesting for these older users here with a high estimated salary. Besides, we can also see that some older people, even with a low estimated salary, actually bought the SUV. Because we can see that we have some green points here that correspond to an age above the average is here, but an estimated salary below the average because the average is here. Okay, so these guys, these older guys, although they have a low estimated salary, actually bought the SUV. Probably because they've been saving up some money, or maybe they finished paying off their mortgage. I don't know, but what's for sure is that they couldn't resist buying this very cool luxury SUV offered at a ridiculously low price. And on the other hand, we can also see that there are some young people here with a high estimated salary who actually bought the SUV. You know, maybe because it's a very cool SUV and they want to impress their friends and take them into road trips, or maybe they already have a family, I don't know. Anyway, they bought the SUV. Actually, there are a lot of buyers, so this must be a very cool and cheap SUV. Okay, and now what is the goal of classification? Now we're talking machine learning. Why are we making some classifiers, and what will classifiers do? At least what are we trying to make them do for this particular business problem? Well, the goal here is to classify the right users into the right categories. That is, we are trying to make a classifier that will catch the right users into the right category, which are, yes, they buy the SUV, and no, they don't buy the SUV. And we represented the way our classifier catches these users by plotting what are called the prediction regions. And so the prediction regions are the two regions that we see on this graph, this red one here and this green one here. And the red prediction region is the region where our classifier catches all the users that don't buy the SUV. And the green prediction region is the region where our classifier catches all the users that buy the SUV. But be careful, this is according to the classifier. That is, for each user of this red prediction region here, our logistic regression classifier predicts that the user doesn't buy the SUV, and for each user of this green prediction region here, our classifier will predict that the user buys the SUV. Even if that's not the case in real life, that's just a prediction, but that's what our classifier believes will happen. It is the classifier prediction compared to the truth here, which is the point. The point is the truth, and the region here is the prediction. So that makes an awesome tool because for each new user of the social network, well, our classifier, our logistic regression classifier will tell based on its age and its estimated salary if this user belongs to this red prediction region here and therefore doesn't buy the SUV, or if this user belongs to this green prediction region here and therefore buys the SUV. And that way, this business client car company can substantially optimize their marketing campaign by targeting the social network ads to the users in the green region because these are the users that are predicted to buy the SUV according to our classifier. Now, the other very important thing to understand is that these are two prediction regions separated by a straight line, which is the straight line here. And the straight line is called the prediction boundary because it's the boundary between the two prediction regions. And the fact that it's a straight line is not random. It is for a particular reason, and that's the thing very important to understand because that's the essence of logistic regression. If the prediction boundary is a straight line here, that's because our logistic regression classifier is a linear classifier. That means that here, since we are in 2 dimensions, because we have 2 independent variables, the age and the estimated salary, so we are in 2 dimensions, then since the logistic regression classifier is a linear classifier, then the prediction boundary separator here can only be a straight line. If we were in 3 dimensions, then it would be a straight plan separating 2 spaces. But here in 2 dimensions, it's a straight line. And it will always be a straight line if your classifier is a linear classifier. But you will see later that when we build non-linear classifiers, then the prediction boundary separator won't be a straight line anymore. I won't tell you more right now, and I will let you wait for the surprise. So here, we can clearly see that our logistic regression classifier manages to catch most of the users who didn't buy the SUV in the red region here, and most of the users who bought the SUV in the green region here. So it actually did a pretty good job. However, it seems to have trouble catching some green users here who, in spite of their low salary, bought the luxury SUV, as well as those other green users here who also bought the luxury SUV. Because as you can see, these green points here and those here are in the red region, which is the region where our classifier predicts that the users don't buy the SUV. And those incorrect predictions are due specifically to the fact that our classifier is a linear classifier and because our users are not linearly distributed. If they were linearly distributed, then we will have all the green points here in this space and all the red points here in this space. And then a linear classifier with a straight line could perfectly separate all the red points here and all the green points here. But here we have some rebellious points who are not in the wanted linear regions, and because our classifier has a linear straight line separator, that's why it has trouble catching those users here and those here. You can clearly see that even if you try to rotate this straight line here, well, you will always have some green points in the wrong category. For example, if we try to rotate here this way, like putting it down, well, okay, we will catch these green points here in the right green region here, but since we rotate it down, we will take more green users here because this will go up and more green users here will be in the red region. So that's the best separator the logistic regression classifier could find, and it couldn't do better because it can only be a straight line separating these 2 regions. Because to catch those users, the green users here and the green users here in the right category, that is the green region, our classifier would need to make some kind of a curve here to, classify correctly those green users here and place them in a green region. And that would prevent our classifier from making this incorrect predictions here because it is a straight line. With a curve here, we would catch all the red users properly in the red region and all the green users in the green region. So that would make an awesome classifier. And you will see how our nonlinear classifiers will make a terrific job at doing this. I can't wait to show you this. Okay, and now eventually the last thing very important to understand is that this is the training set. This is a training set, so that means that our classifier learned how to classify based on these informations here. So I would hold my breath a few more seconds until I find out if our logistic regression classifier can manage to make good predictions of new observations, that is to classify new users into the right regions, which by the way are fixed regions here because these are the regions generated by the learning experience of our logistic regression classifier and therefore won't change if we look at some new observations, that is new social network users. And that's what we are about to find out on the test set. So hold on. So it's very simple. We're just going to copy all this code section here, paste it here, and I'm just going to change the training set here by test set. Same here, I changed training set by test set, and that's all. That's all because I structured the codes in such a way that we only need to change the training set into the test set here to plot this graph on a specific set. However, let's change the title here because we want to specify that it's the test set and it's ready. So let's select this and execute. Let's see what happens. And here are the results of the test set. So that's not too bad. That's not too bad because as we can see, the majority of red points are in the right region. That means the region predicted to be 0. And the majority of green points are in the right region. As for the training set, there are some observations that were incorrectly predicted, but that's normal. That's because it's a linear classifier and it cannot make a curve here catching all the right guys. And remember, in the confusion matrix we counted 10 plus 7 incorrect predictions. And if you want to count the incorrect predictions here, you will find 17 incorrect predictions. Alright, so that's it for the interpretation of the graph. I can't wait to show you how we can make more powerful classifiers. So it's going to be in the next sections. And of course, these are going to be nonlinear classifiers. So for those of you who are interested in knowing how the code works, stay with me, I will explain that. So I will reduce this. Okay. And let's explain this. Okay. So the idea is that we consider each of these pixel observation points as a user in the social network, like an imaginative user. And so, for example, this pixel point here is not a user in the dataset, but we imagine this pixel point here as a user who has this salary and this age. And we apply our classifier on this pixel observation point, on this user here, so that the classifier predicts if the user is going to buy yes or no the SUV. Then once the classifier makes its prediction, it colorizes the pixel observation point according to the prediction. So if the prediction is no, this pixel user won't buy the SUV, then it will colorize in red. And if the prediction is yes, this pixel user will buy the SUV, then it will colorize the points in green. And so we apply that idea on all the pixels in this frame, so that eventually our classifier will colorize all the points that he predicted as 0 in red and all the points that he predicted as 1 in green. So now that you get the idea, let's look at our code here and go through the steps of completing this idea. Okay, so first I declare set equals training set. That's because, I want to plot this graph for the training set and the test set. And since we're using training set many times in the code, I just replaced it by set here, so that when I copy paste the same code for the test set, I just need to replace test set by training set only here and not in the whole code. So basically that's just a shortcut. And so first we build a grid with x1 and x2. So we take the minimum of the values of the training set minus 1 because we don't want the points to be squeezed in the graph. And same for the maximum, plus 1. So by doing this, we're taking the range of our training set observation points, minus 1 and plus 1, so that our points are not squeezed in the graph. And so we're doing this for the age column of the training set and the salary column of the training set. Then by writing this line, we are building the grid. So basically with these 3 lines, we're making the grid here with all the pixel observation points that are imaginary social network users. Then since this grid set is actually a matrix of the 2 columns age and salary, but for all the imaginary users that are the pixel observation points, this is actually a matrix. So with this line, we just give a name to the columns of this matrix, which are age and estimated salary. And then that's where all the magic happens. Because here, that's where we use our classifier to predict the result of each of the pixel observation points that are the imaginary pixel users. So we predict this, and then, since the predict function returns the probabilities, we transform it into 1 or 0 result. So that's why I call it Y-grid, because it's the predictions of all the points in the grid. So that returns the vector of predictions of all the points in the grid. And then finally, we plot the whole graph. So in this plot, we include all our real users and their real actions. Red if they didn't buy the car, and green if they bought the car. And we plot the predicted results of all the pixel observation points that we created when we created the grid. So that's here. And so, I'm using the color spring green. So that is the spring green color. And tomato, that is the tomato color. And for the real points, I just use a green 4, which is a color in R, and red 3. So this color is green 4, and this color is red 3. And that's it. That's the idea behind this code. It's totally fine if you didn't understand some things in this code, because anyway, we're going to use this code as a template for our next classifiers. And so we'll just have to copy paste this code, but that's all. So that was just for those of you who are interested in coding, who are interested in how we can use code to make such a plot. But the important thing to understand here is that the logistic regression is a linear classifier, which in 2 dimensions means that it's a linear separator, and therefore it can miss some predictions, like the predictions here, that are incorrect. Alright, so thank you for watching this R tutorials, and congratulations, now you know how to implement a logistic regression model using R. This is the beginning of our journey in the classifiers world. You're going to see that we will meet some more powerful classifiers later in our journey. So I look forward to continue this journey.